You guys are... Wait, just stop. You guys just grab. We chose to do golf for our physics project. There's a lot of physics involved in golf, such as we can find the distance that a golf ball has traveled using a rangefinder, and we know the angle of all of the clubs. So we can figure out the apex and the velocity of a golf club.
Golf is a great example of projectile motion. You hit it, it goes in the air, and gravity takes it right back down, so we figured golf would be perfect for this project.
And you'll notice our safety features. Everyone's wearing proper equipment such as safety glasses. Chuck's got his helmet on and he's got his safety vest, so we know we're not going to run into safety concerns. Oh, get in the hole!
You're gonna get hit. Oh my god.
So one of the things we experienced while we were doing this was air resistance plays into the equation. As the ball is in the air, it's going to be getting pushed back on with drag. So that is something that we did not necessarily equate for.
And one of the features on a golf ball is dimples, and that helps to reduce the air resistance, but we know that it doesn't completely negate the air resistance.
Another difficulty we possibly could have faced during this was that the rangefinder we have only is accurate up to about 320 meters, and even still distances below that we can't be 100% sure that it's accurate to the very last meter. Okay, so some of the data we collected during this video was our initial angle was 60 degrees because we used the lob wedge and that comes on the club. So that's one of our givens. The distance we measured was 60 meters when the ball landed. Gravity obviously is 9.8 meters per second squared, accelerating downward towards the earth. And the time we took for the ball from the time it left the ground to when it hit the ground was 4.6 seconds.
Solve for our initial velocity. What we have to do is we have to take our gravity times our, which is right here, times our total distance, and then put that over 2 times the sine of our angle, which was 60, and the cosine of our angle, which is 60 degrees. So that simplifies out. When we plug everything in, you get 9.8 meters per second squared times all of that. It comes out to 588 meters squared per second squared over 0.866, which then simplifies to be square root of 678, and that comes out to be 26.057 meters per second for our initial velocity.
Okay, to solve for our max height, we use the equation height equals 1/2 times gravity, which is 9.8 meters per second squared, times time, which is 4.6 seconds over 2, that quantity squared. And this comes out to be the max height as 25.921 meters.
Okay, so the data we collected for the 7-iron, the angle changed. The angle is now 34 degrees, which allows it to go farther, and it reaches a lower maximum height. The distance we found was 132 meters. The time it took to get there was 4.3 seconds, and gravity stays the same at 9.8 meters per second, acting downwards towards the Earth.
So for initial velocity, it's going to be a very similar process. The only difference is we're going to have a different distance. We're going to have a different angle. So we plug 132 now into the equation and 34 degrees in for our sine and cosine configurations. So that's going to give us 1,293.6 meters squared per second squared over 0.927, which simplifies out to be 1,395. Square root of that, we get 37.352 meters per second for the initial velocity.
So the equation for max height is the same as before. The only thing that changes is the 4.3 seconds that it took from the time that the ball was struck to the time it hit the ground. And we get a new max height of 22.65 meters. And this is the graph that shows the max height.